Hello, this is Kaelyn. Today I'll be walking you through the code we use to perform our matrix multiplication performance comparison. We will be looking at CPU implementation and 3 GPU programs, naive CUDA, tiled CUDA, and the cuBLAS library, which is NVIDIA's own library. So we're going to start with our CPU implementation, which serves as our baseline. We have basic matrix multiplication. The outer loop goes through each row of A, and this loop goes through each column of B, and the innermost loop K multiplies and accumulates the products that form one element of the result matrix. It's stored in C. So A and B and C are all initialized. A and B are randomly generated, and we measure the time that it takes for the calculation to happen, and that is our CPU program. So going on to our native CUDA implementation, it's comprised of two parts: the device code, which is the GPU code, which does the calculations, and the host code, which we use to initialize and create the random matrices, just like in the first code. So the key difference is that our GPU is doing our calculations, and so in our basic matrix multiplication, each thread needs to find the row and column, does its own dot product, and writes the result back into the global memory of the GPU. And these can be calculated in parallel because multiple threads can be running. So here you can see we define the 16 by 16 thread per block, which is 256 threads, and we compute right here how many blocks we need to cover the whole n by n matrix. Right here we are launching our kernel on the GPU, so each thread can compute a single C row and column. And so we just calculate how long it takes for the calculation to occur. For the tiled CUDA, tiling uses shared memory, so it's much faster when you're accessing the memory space and reduces redundancies. So the shared arrays act like local caches that store small tiles of A and B, so we can reuse them, but it uses the same basic function for matrix multiplication of each C element. What's happening right here is each block of threads loads one tile of A and one tile of B into a shared memory, and they sync to make sure the tile's ready and no threads are redundantly calculating an element of C. Each thread multiplies and accumulates within its tile, and that repeats for each tile in the matrix. On the host side, the kernel call looks the same, but the performance is improved a lot because we don't have to call elements from memory as redundantly. And for larger matrices, this can be very advantageous. So the cuBLAS library does all of this tiling in the library. We just set it up. Right here is where we use the library. It automatically handles tiling, memory coalescing, and instruction level optimization. All we have to do is set up the matrices on the GPU like we did before in the other code, and we measure the time that it takes to execute this. We also have to swap B and A because cuBLAS uses row major. cuBLAS is usually the fastest because it's tuned by NVIDIA's engineer for every GPU generation. So looking at our results, we have on the X the matrix size, and this is our execution time comparison. So on the Y we have our execution time, and you can see CPU once we get to this is 256. Ooh. This is 256 right here, and it doubles at each point. So that's why it's increasing logarithmically. By the time it gets to 512, then the GPU is going to be outperforming the CPU because the GPU can do it in parallel. So the blue line shows the CPU performance. The orange line is the naive CUDA kernel, and the yellow line is our optimized tile version, which is slightly better than the naive, but this one is not fully tuned for the size of our GPU. Then the purple line represents our cuBLAS, which you can see for the larger sizes it scales well. The CPU is the slowest because it executes operations sequentially. The naive CUDA introduces massive parallelism. The tiled CUDA adds shared memory for better efficiency, and cuBLAS uses NVIDIA's full optimization stack.
Hello, my name is Ravi, and this is ee542 lab6, high performance CUDA programming on Google Cloud. The lab is divided into two parts, wherein in the first part, we compare the performance of GPU and CPU for general matrix multiplication. The second part is where we compare the performance of, again, CPU and GPU for image processing, wherein we convolve image processing kernel on an input image and we receive an output image. I'll go over what basic matrix multiplication is and what convolution is. I'll go over their concepts and then I'll hop onto the code for convolution for image processing. So this is the basic matrix multiplication visualization. So we have a matrix A with dimension n cross m. We have a matrix B with dimension n cross n, and we receive an output matrix with n cross n when we multiply A and B. We know that the inner dimensions are dropped when we multiply two matrices, and we retain the outer dimensions. Now, to calculate any calculate any element of the output matrix, we use this closed form solution, which is the sum of product of elements of A and B. Here, element AIK represents the element of A matrix at the ith row and the kth column. BKJ represents the element in the B matrix with the kth row and the jth column. So the product is summed over k equal to 1 to n. K is the inner dimension, and we can clearly see that the uh, k variable is changing through the loop, while I and j are loop invariant, and uh, throughout the loop they do not change. We can see that when we multiply the elements of A, the row 0 does not change and column 0 does not change whenever we are trying to calculate. Sorry, row 1 does not change and column 1 does not change of B whenever we are trying to calculate the element C11. Now I'll quickly go over what CUDA is and what convolution is. So, so the basic execution unit in CUDA programming is a CUDA thread that represents a CUDA core uh, on hardware. Multiple CUDA threads are called thread blocks, and they represent a streaming multiprocessor. Multiple CUDA thread blocks represent a grid, and it represents the 3D uh, die of the GPU. CUDA threads are run in parallel, and one streaming multiprocessor handles shared memory, wherein all the CUDA cores share this memory and execute tasks parallelly. This is a CUDA grid representation, wherein grid dimension y represents the number of blocks that we have in y dimension of a grid, and grid dimension x represents the number of blocks that we have in the grid uh, in x dimension. Now we can see that we have 3 blocks in the x dimension and 3 blocks in the y dimension. We name them as such: 0, block 0, block 1, and block 2. Now, this naming is accessed by block index of the blocks, and we get the uh, indices of these blocks in x dimension and y dimension correspondingly. Now, each of these elements in the block are CUDA cores that run CUDA kernels, and they run it parallelly for single instruction multiple threading. And this is single instruction multiple threading. This is the corresponding 3D layout of the grid. We have the Z dimension as well. The Z dimension here shows that we have 4 CUDA thread blocks in the Z dimension. Now I'll quickly go over what convolution is. Convolution is nothing but multiply and accumulate, wherein we multiply the element of the input to the corresponding element of the kernel, and then we add all of those multiplications and we get the resultant output. So I'll let the animation complete and you can see what's happening with convolution. So basic image processing is nothing but input image convolved with image processing kernels, and that's how we get the output image. Now I'll quickly hop onto the code. This is the matrix library.h, which contains all of the functions, kernels, CUDA kernels, and image processing kernels for our convolution operation. We perform 2D convolution, and this is what we do. So this library contains the uh, important matrix multiply CUDA kernels, matrix multiplies CPU functions, and it also contains the image processing kernels that we would be using. in matrix lib.cu file. This is a CUDA file, and one key thing in this, that we utilize for optimization of uh, convolution is tiling. Tiling is nothing but using the shared memory of the streaming multiprocessor to improve our efficiency of convolution of our operations and increase the throughput. So what tiling does is it takes a part of a matrix and it stores it in the shared memory. It takes a part of matrix A and it takes a part of matrix B, and that's how uh, we would every CUDA core would access the elements of matrix A and matrix B. The motivation behind tiling is that DRAM is very slow in getting the elements, and whenever we call a CUDA kernel, we access that element multiple times, and every CUDA core has to wait for the element to reach from DRAM to the streaming multiprocessor, and then the CUDA core would be able to access the element. Instead, tiling uses the approach of bringing all of the data to the shared memory of the streaming multiprocessor. Now, the GPU that we are using is V100, which can handle 32 watts in one dimension at a time, in X dimension and in Y dimension. That's why we use a tile width of 32, and we bring in 32 rows and 32 columns of matrix A and matrix B into the shared memory of the streaming multiprocessor. Now, this is the CUDA kernel that would be running for matrix multiplication. We take in the uh, pointers for, I'm sorry, the pointers for the uh, which were assigned on the device, and we take in the number of elements that the matrix has in one dimension. Shared memory is the way to store data that is shared between threads in a block. We use shared memory to store the tiles of the matrices A and B, so we can access the data faster. This is how we uh, initialize the space on the shared memory. We initialize a 2D array with dimensions 32 cross 32, as tile width is 32, as I mentioned. We do the same for the B matrix, and this represents device shared matrix B. Device here represents the GPU device, and the host represents the CPU. We after we've after we've assigned spaces for these matrices, we get the block index and the thread index to know which tile we are working on. Row and column Row and column here represents the global index, represent the global index of the tile we are working on. Now we also have to remember the property of matrices, the block matrices, wherein we can divide a matrix into subblocks and we can perform operations like addition and multiplication. Now we assign the partial sum value because every block matrix would be multiplying and accumulating a value, and this is a partial sum value. That's why we require a partial sum variable that would uh, that would go through every tile, and it would accumulate all of the computations uh, for a single output element of the C matrix. So we loop through the tiles of matrices A and B. Here M is the tile index, and it loops through the matrices until we reach the end. We load the tile of the matrix A, and this is how we load it into the shared memory. Similarly, we do it for the B thread as well. Now, the important thing is that every CUDA kernel would be loading the memory from uh, from the DRAM to the shared memory. And now it may so happen that some threads are slower and some threads are faster based on how they get access to the DRAM. And we need to synchronize these threads to ensure that the tiles are loaded before we start the multiplication. So sync threads, what it does is it ensures that all the execution states of all the threads, all the CUDA cores is uh, all the CUDA cores are on the same execution state. Then we multiply the tiles of matrices A and B, and we store it in the P value, which accumulates uh, operations for each tile. We sync the threads after the multiplication is done, so that this ensures that all of the CUDA kernels have executed and they are uh, done with the matrix multiplication. And now we are able to store all the accumulated value uh, in the C output uh, matrix. Now, this is the C function for Python. We use Python for image processing. So this would be called in our Python file. I'll go over it once I'm done with this. So this is run into in the CPU. That's why we have pointers for the matrices as HA, which means host matrix A, host matrix B, and host matrix C, and the n representing the dimensions of the matrix one uh, in one dimension. We declare the size of the matrix that we want to uh, store the matrix that we want. We allocate pointers, uh, and then we allocate memory to these pointers. Once we are done with allocating memory on the CPU, we then allocate memory to the device as well, which is the GPU. And then this is how we launch the kernel. This function represents CPU convolution with timing. Now, we would be calling our convolution kernel that I showed you earlier for multiple filters. And we need to reduce redundancy, we created a convolution 2D CPU, which would run the convolution for multiple filters and measure the time on the CPU. We start the clock over here. This function is used to convolve the image with the filter. It's a 2D convolution. It is a convolution of image with the filter, and the output is stored in the output image. The output is the same dimension as the input image, but with the filter applied onto it. We get half of the filter size, half of this filter. Uh, because we want every element of the filter, every element of the kernel of the convolution kernel to properly map to every element of the image. We to use you perform this logic to loop over the image and over the kernel. We loop through the image and apply the filter to each pixel. Y is the row index and X is the column index. M is the size of the input and N is the size of the filter. Now, by looking at the code for the CPU, you can clearly see that the time complexity is really high. And that's why we need GPUs for convolution, because GPUs are very good at multiply and accumulate um, for parallel tasks. First, we initialize the sum to 0. This is the sum of the products of the filter and the image. We loop through the filter. We get the pixel of the pixel indices. We check if the pixel index is within the image range. We get the pixel value in, and it and it with 0xFF just to get the last 8 bits. Now we are focusing on working with grayscale images. That's why we mask the image values and just take the grayscale value. And this is how we get it, just by adding the image pixel values to 0xFF hex code. We get the corresponding filter value, and we a- add the product of the pixel and the filter to the sum. This is the multiply and accumulate part of the convolution. Now, this is thresholding, which means we are thresholding the values, that the output values, either to white or either to black. We set the sum to 0 if it is less than 0, and to 255 if it is greater than 255. We write the result to the output image, and we typecast it to uh, typecast back to 32-bit integer, which shows the RGB image. But when we will actually be showing, we would be showing grayscale images. We measure the uh, time taken for the convolution to happen, and we uh, print out the time taken to convolve. This is the CUDA 2D kernel. Similarly, for CUDA, we perform the execution of convolution. And you can see just by looking at the code that the complexity is reduced to n square, because we do not have to loop through the image, and we just have to loop through the filters, because looping through the image is not required, as CUDA would be handling uh, each pixel of the image, and we just have to loop through the kernel. We do the thresholding for the CUDA kernel as well. Now, when we are calling the convolution to 2D CUDA code, we would be calling it for multiple kernels. That's why this function handles the timing, the memory allocation, and the displaying of how, mu- uh, how much time took to uh, perform 2D convolution using the CUDA kernels. These are the filters. This is the edge detection filter. This is the raised effect filter, which is nothing but it increases the contrast of the images. And then we have the shading filter. This is a directional shading filter, which represents light from the top left. And we can see in the implementation, and Aqib will show the implementation for that. This is just a process image function that goes over the execution of convolution for different filters on the images. This is the Python script that we run to perform 2D convolution on different sizes of images, and the implementation would be shown by Aqib for this. We just load the shared library. So everything should be in the shared library, and we load the folders and the files in the shared library. We set up images. All of the images should be uint32, and we set up the images over here. This is the we create the output uh, directly, and we then call the process image folder, which calls the uh, process image function from our matrix library. And this is how we do the implementation for convolution, and uh, Aqib will go over the uh, impl implementation of convolution.
Hi, I am Syed Aqib Haider. I will be explaining the demonstration of our program for lab6 CUDA programming. So this is my GCP console, and this is my instance in which I have installed this. This has a GPU V100 from NVIDIA, and it also has Jupyter, on which we will be working as the interface. So as you can see, I have it running, and now I'll have to connect it both in a terminal window as well as GCP. So I'm going to do that, and then we'll go through all the programs. So we authorize this. Now here we can see we are in the base environment of CUDA, of Jupyter, but all our programming and CUDA is enabled on another environment which is test CUDA in Conda. So we activate that environment. The name of the environment is test CUDA, test underscore CUDA. So we have it activated. Now 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 there is another command that we need to give, which is this command: Jupyter notebook, no browser, port 8888, or any port that we like. After this, we need to copy this command: gcloud compute ssh instance with our instance name and zone and this flag, and give it into the Google Cloud shell. This will open another terminal that will be our, we accept this, and we will be working on this terminal, but we'll have to switch the user from my username to Sayyid Aqib, because as we can see, if we do ls here we see nothing, so we'll have to switch the username. Okay, so here we have our instance. We just switch the environment. And now if we see, we have all the files that we need. We have this images folder in which we will be doing our images processing. And let's just try to connect Jupyter. The way we connect Jupyter is, after all those commands were for enabling us to connect to Jupyter using localhost 888. So here we can connect it. So as we can see, these are the files. So as explained, we have a couple of files. First we'll try the naive CUDA, which is the file matrix multiply jupyter.cu, and it has already been compiled into matrix multiply Jupyter. So we just do that. Matrix multiply underscore Jupyter, and we can give, if we don't give an argument, the matrix size, it assumes a default of 1024. So let's just do that. So n is 1024, naive CUDA, it is, time is 1.126 milliseconds. And if we give 512, we see it's 0.153. If we get 2094, sorry, 20, it should be 2048, sorry, it's 9 milliseconds for 2048 matrix size. For 4096 it is 74 milliseconds, and for 8192 it should be more than that, roughly 500 milliseconds. Yeah, so it is 576 milliseconds. This is the naive CUDA. Now we have another file here, matmul underscore tiled, which is, I don't know if it's compiled or not. And we see, yeah, we have this matmul tiled, which is it is already compiled, so we should just use that. Matmul underscore tiled. We use it without without an argument. It takes 1024. So here it takes 0.6 milliseconds compared to 1.126 for a naive version of CUDA. So roughly it gets halved. So just to check that it is same, we do it. Yeah, it is roughly the same. So basically by default it takes 1024. For 512 it takes 0.1 millisecond, which is rough, not half of 0.153 naive CUDA, but still less than roughly 40-30% less than naive version. If we do 2048, probably when the matrix size gets smaller, the factor of half is gets reduced. Okay, so 2048, it's 4.8 compared to 9.1 for naive CUDA. For 4092 it is the tiled version, basically the shared memory version, the optimized CUDA version. It takes 38 milliseconds compared to 74 for 4096. Let's just check for 8 kilobytes. Sorry, 8 kilo values. So it takes 284 milliseconds, which is roughly again half of 576. So this was the optimized shared memory version, matmul underscore tiled. We have another file that is matmul underscore cuBLAS that uses cuBLAS library. So do we have that file, matmul? Yeah, we have matmul cuBLAS. So just underscore cuBLAS. Don't do anything. It takes 1024, but the first time we run it, it often gives a longer value, maybe because of loading of some data. It takes 23 milliseconds. Let's just run it again. Yeah, it takes 0.9. Run it once more. It takes 0.9. So for cuBLAS, in case of 1024, it takes 0.9 milliseconds, and in matmul shared version it takes 0.6 and 1.1 for the naive CUDA. Let's just see 2048, we're 512 version. It takes 0.828, even more than the naive version, maybe because as the sizes decrease, it's not so efficient. Now 2048 version of the matrix size. It takes 2.2 milliseconds, and 2048 takes 4 milliseconds for tiled shared memory version and 9 milliseconds for naive CUDA. Now cuBLAS takes approximately, for 4096 it takes 11 milliseconds, and 4092 it takes 38 milliseconds for shared version and 74 milliseconds for naive version. Let's see 8192 version. 8192 192. So it takes 83 milliseconds, while the shared memory version optimized CUDA takes 284 milliseconds, and the naive version takes 576 milliseconds. So this was about optimizing CUDA. and how we can optimize it using shared memory and pre-written libraries like cuBLAS. And now we will try to see how to compile a library and use it in Python or CUDA as well. So as we can see here, there is a matrix lib.cu that gets eventually compiled into libmatrix.so. I think it is already compiled, matrixlib.co. But even if it is not compiled, we can compile it with this nvcc command. So this is the command we use: nvcc x compiler fpic shared matrix lib.cu. This is the name of the uh, shared.so file that will be created. It should start with lib, and we do this. It's compiled, and .so file matrix. Now let me just see. Can we see matrix lib.so? Yeah, we have this matrix libmatrix.so. And now we can call this in a Python function, which we have written here. Python matml shared library. So this is the code. We import C types, numpy, time, and here lib, we load this library. So we run this. Here it is n is equal to 1024, and this is the definition of archetypes. And now it calls the matrix multiply, which uses CUDA of the library version. Yeah, and it takes 0.3178. We could change the arguments. 0.0024, 2048, 0.0304, 4096, 0.1414 seconds, roughly 141 milliseconds. Let's just do 8192 also. So 0.6 seconds, that is 666 milliseconds. So this was basically demonstration of calling the shared library from Python. And now we move to the image processing part, which also uses this libmatrix shared library, because it has this library also has the convolution and filter functions, as well as process images functions that we will use, and we will call them in a CUDA file as well as a Python file that we have. This is the process images.CUDA file and process images Python file. Both of them use the libmatrix.so file, and it operates on these images folder. Oops. Okay. Yeah. So these are our outputs: images 128, 10 images of 128 by 128, 10 images of 256 by 256, and 10 images of 512 by 512. These are our images. Rest all are outputs that I will delete right now to demonstrate. Just shift. So I'll just delete them so I can. This is what is created after running the programs. We're not deleting the input images. Move to trash. Okay, so like this is the image, one image, and this is another image. Similarly, there are all these images. Let's just see some image of this is image for 256, some images of 256 and all that stuff. So these are the input images, and we will process them using some filters both from Python and CUDA. So we have compiled the shared library, but in order to be able to call this, we need to, so that CUDA can call it, CUDA and Python functions can call it, we need to add it to the path, add its path to the LD path, library path environment variable, and for that we have a separate command which is this command, export LD library path. So we add the current library into the current environment variable load library path. So with that done, we can start with our processing of the images. So first we shall demonstrate .cu process image, and then Python process image. So if I just do that, it will give me the usage. Process image. I think it's still not. Oh, it's process images, I guess. Yeah, it's process images. Sorry. So because I've not given the arguments, these are, it is giving me the usage. So here I give the process images, then image size. So there are three options: 128, 256, 512. Let us just try say 128, and a filter size, it could be any odd number, and the other function is 0 or 1, 0 for using CPU, 1 for CUDA, and the last argument is for the type of filter. We have three filters. One is edge detection, other is raised, and the other is shaded. So let us just try a few of them. So process images 128. We'll process the 128, 10 images of 128 by 128. Filter size, let's just say 5, and let's just use CUDA, and let's just say edge detection. Done. Now I shall try raised. Okay, and shaded version. Okay, so now with these run, we will see output images in the images folder. Here we have, so the output is named as follows: output underscore the type of filter, edge, raised or shaded, and then image, then the number which denotes image size, then filter size followed by the value of that filter size, and then whether it's CUDA, C, or C via Python, or CUDA via Python. So let's just see how it is. So oh, it's like the Golden Gate Bridge with edge detection version. basically this is the original image and this is the edge detection version with filter size of 5. Now let's just see shaded version. This is the actual images version, I guess. Yeah, shaded version. This is the embossed or raised version, not the shaded version. And see the shaded version. This is the shaded version. Let's just see some more images. Like this is the shaded version for 128.5. Let's see how it actually looks like. So it looks like a little blurry original version. That's why it's blurry here even. So this is how you do the call it from CUDA. We could also do it using C version. It just takes a little more time. For example, here it takes a very less time, less than a millisecond. Well, you know, 0.5 millisecond, 0.4 milliseconds, 0.4 milliseconds. Well, if I increase the image size, it would take some more time. Let's just see edge detection with 502 version. This is still CUDA on 512 and it takes 2 milliseconds. Now let's just see it, how much time does it take on C. So running C program on 10 images of 512 size with edge detection, and it takes slightly more time. It takes 47 milliseconds as compared to 2 milliseconds in case of CUDA. Let's just see the output. So here we have output of 512 for C and CUDA. They should be the same because the filter is, I guess, the same, edge detection. Let's just see. Now here's the output, edge detection, and for C it should be the same. This was image 512 4. So 512 4. Yeah, it's the same. We can just see how the actual image looks like. It's 512 4. Yeah, it's a cup. So this is the edge detection version. Let's just see how the other versions look like. I'll just go with CUDA, it's faster. This is the raised version because filter size 1. Raised effect filter is 2. Shaded effect filter. Let's just see, this should be available. So 512 shaded and raised. Raised image 4. Yeah, that's nice. Yes. This is the raised effect, and we shall see the shaded effect too. Yes, this is the shaded. This is the shaded effect. Now we could also call the same functions with the Python script of process images.py. So we just have to give Python 3 process images.py. Now it also has some arguments, which if we do not enter, it will give us the usage. See, so Python 3, image size, filter size, CPU, basically the same. So let me just try the same version, 512. Filter size, let's just try filter size of 7, and the C version, and edge detection. Okay, so it takes roughly 87 milliseconds. Now the raised version, the raised embossed filter version with filter size of 7 and 512 image size. Oh, and by the way, these are basically for processing 10 images, all these image processings. It takes 85, and should see similar because the type of filter doesn't go doesn't really significantly alter the processing time. So both of them, 87, 85, 84, broadly the same. Let's just try with the CUDA version. Edge detection with CUDA. Okay. And edge detection with CUDA, raised effect with CUDA. Enter. Yes. So 0.17, 0.02, as we can see, it is about 4 to 5 times faster, because here it takes 84 milliseconds, here it takes 21 or 17 milliseconds. And then shaded filter, yes, so the filter size here is different, so we'll have another folder. Let's just close a bit of them. Okay, so here we have C via Python, CUDA via Python. So let's just see edge detection, C via Python. Anyone? Say 6. So 6. This is the edge detection. Let's just see how the actual image looks like. 6th version. So okay, so this is what the actual image looks like, and this is edge detection version, and this one's not so graphic, so let's just select this one, see how this looks like. They all look pretty much similar. Yeah, 7th one looks like this. Let's just see how CUDA version looks like. Yeah, it's pretty much the same. They should be the same because the processing is the same, only it's the time that. Okay, so here's the raised effect filter. And let's just see how the shaded version looks like. This is the shaded version, this is the raised effect version, this is the edge detection version. So this is how we can run these programs for these filters. Now I do have a shell script that runs across various configurations. We'll go through that shell script and then we'll run it. So this is the shell script. So basically it gets the timestamp, gives two kinds of logs, full log and short log, and then it runs over these sizes 128, 256, 512, these options 0 and 1 for C and CUDA, filter size, filters 0, 1 and 2 for edge, raised or shaded, and then it runs across these filter sizes from 3 to 13 in odd, 3, 5, 7, 9, 11, 13, and these are the programs. And eventually it associates the name filter names with these indices, and then it runs across all possible configuration in programs for Python or C, then sizes of the image sizes, then option C or CUDA, then filters, which one, raised, edge detection or shaded, and the filter size from 3 to 13. It runs the Python script and the CUDA version, and eventually stores the output in a log file. So we shall run that. Dot, what was the name? Plus, oh, and by the way, the since Linux overwrites the file, we don't need to delete them. It will be overwritten automatically. These folders that we have just created. So it is run images.sh. Yes. So run core images.sh. So once we run that, it will run across all possible configurations, and here we go. As we can see, as it is C and the largest file, so it takes a little more time to process. For CUDA, it doesn't take much time. Now it's running C via Python on 128 image size. Now CUDA via Python, lesser times. Again, C via Python on 256, taking more time. Again, this will be long because C via Python on 512. Okay, so we are done, and it says we have the short and long summary. Actually, our concern is full. The short one just is not our concern. 202510062448. Let's just check it out. Close this, close this, close this, close this, close this, close this, and 2314484. Full. So this basically gives our values running C program on 10 images 128, filter size 7. And from here it goes all the way to, it should be CUDA via Python on filter size 13 and 512 image size. Yes, 512 image size, shaded filter. Here is the time that it takes. This is kind of log file, and we will have lots of folders in the images folder for output. So here we see we have output folders of all configurations. So let's just check randomly some. Let's just see how a bigger filter changes it. So it's CUDA 12. Let's just see how it. This is nice. That's the cup, right? So this was all for the demonstration of our CUDA programming and using it for image processing. And we can check the timings also. Basically, CUDA accelerates it. So if we just compare two, this was our file, say for C program on 10 images 128 on filter size 11 by 11. Let's just check how much CUDA takes on 11 by 11 and 128. CUDA, here it takes, yeah, CUDA on 128 11 by 11 takes 0.4 milliseconds, and 128 C program 11 by 11 takes 12 milliseconds. So this was just a rough example, one sample of how CUDA accelerates from 12 milliseconds to 0.4 milliseconds for operating over 10 images. So the other number should match too, and which should be given in the report. So this was all from our side. Thank you so much.